Yeah, so thank you everybody for coming this morning, and we're delighted to have Marina Meila from University of Washington giving the next mini course this morning and tomorrow. And so we'll figure out what to do and alert you to the change in schedule for her other lecture from this morning. So we'll keep you posted by email. And yeah, so she'll be talking about a tutorial for manifold learning for real data. Thank you, Marina.
Thank you very much, everyone. Not the least for your patience and for the disruption that my being late caused. This is an actual lecture. It's going to be, I'm going to write on the board, on my virtual board, and you have been emailed the lecture notes just now. The lecture notes contain certain notes that are not going to be in the slides. Yes, so they're much busier than the slides, and you can use them either simultaneously or if you want to reread the notes. Also, because the time is slightly shorter, I'm going to compress some topics, but definitely not the beginning, because it's important to start on the right footing. That's the goal of a course. So without further ado, let's talk about manifold learning. The first thing is, why do we do manifold learning? When I teach this in class, I invite students to tell me first what they do, what they're doing, what is it that they do principal components for. And I want to say that this time I'm not going to invite questions at this point, but I hope that chat is enabled for the students as well. And I hope that there will be some questions now and then, like interrupting me. So feel free to ask questions for clarification. We are all here. I am here to teach and you are here to learn. And I want you to leave with as little confusion as possible after this class. So I'm going to start by enumerating a few reasons why people do perform principal components analysis. And one of them is because the data is high dimensional and they want to reduce it to low dimension. And that's because this means saving space and maybe processing time. And maybe other computational savings. But doing principal components is not the only reason people, but computational savings is not the only reason people are doing principal components. It's also to better understand high dimensional data. Yeah. And also because understanding is equivalent to finding more relevant features in the data. And I'm going to put it in quotes because we don't know what relevant is at this point. We haven't defined it. And therefore, when principal components is, when this data is fed to algorithms, in other machine learning algorithms or other data analysis algorithms, they will have a better view of the data, a more relevant view of the features, better features in the data. While I was talking, you may have thought of other reasons why people do principal components, which is actually linear dimension reduction. And all these reasons also apply to manifold learning, which is nonlinear dimension reduction. Now I want to show you a few of the examples, real data examples that I want you to have in mind as we go through the to the actual lectures. So this example is from a Sky survey that lasted more than 10 years and ended recently. And this is just a small part of the data collected in the survey. They collected spectra. And this is a spectrum. This is the light spectrum of a galaxy, and you can see here that these are frequency bands. It is not important that you read this. What's important is that this spectrum is a very high-dimensional vector. It has about 4,000 dimensions. However, if we do nonlinear dimension reduction, manifold learning, and this is a diffusion maps algorithm, if you have heard of it. Then we can see that this data lives really in only 3 dimensions. And moreover, even though the data is embedded, and I'm going to explain this term in 3 dimensions, really much of the data lives in 1 dimension. However, there is noise around these one-dimensional manifolds. Yeah. So this is one example of physical data that we may use. Keep it in mind. Another example that we're going to use much more, in fact, I'm going to use it for illustration, is in the space of configurations of molecule. So this is the molecule of aspirin. It has 21 atoms. Each atom has has a 3D coordinates. So this is about 63, it's slightly near, so this is near 60 dimensional space, each configuration. And if we look in two of these 60 dimensions, we see this tangle, like this tangle here. After we do some pre-processing and manifold learning, we get something that looks like this. We get 2 shapes, 2 manifolds that look like noisy, distorted tori. One torus and the other torus. And the reason you get 2 and not 1 is shown in the first coordinate. This is the first manifold learning coordinate. And it's not really a manifold learning coordinate after all. It's mostly a step function. Yes. And this step function indicates which of the states belong to the manifold on the left and which to the manifold on the right. Yes. So this is a dimension reduction that's slightly more complex, but you should be prepared to encounter it in the data, where in fact there are 2 manifolds that are almost independent. So there is both a low dimensional structure that is reflected by the manifolds, but also but there is also a clustering structure. And so the first coordinate in manifold learning gives us the separation, the cluster separation. And we have to go up to coordinates 2, 3, 4, 5, 6 to find the 2 manifolds. So even though this data is essentially 2-dimensional in each cluster, we need a space of dimension 6 to discover the complete structure, low-dimensional structure of these data. Yes. So what I want you to keep in mind is that very often the data on the manifold is clustered. And in that case, we have first a form of spectral clustering problem. And after that is solved, and typically this is going to be easy to solve in manifold data. As you see here, like this is real data and it's as clean as it could get. So after that is solved, we have to return to the manifold learning problem as in the textbook style. Yes, so real data is always slightly more complex than what we expect. Another thing that I want to point out here is that the data is noisy. And in real data is always noisy, it's never exactly on a manifold. The algorithms I'm presenting and most of the algorithms in literature are actually about non-noisy data. However, part of the experience, and I'm going to say it up front, is that the manifold learning algorithms are really good at smoothing this noise out. So I'm going to give you a lot of bad news and a lot of warnings near the end of the talk about what you should be worried about when you run a manifold learning algorithm. But there are also good news that this manifold algorithm works and they do denoise the data. And so they do work in the data, whether we have proof of that or not. Okay. So one more motivational slide. This is another real data set, but it's a toy data set. And you'll see it again and again. Maybe you have already seen it before. Each of these points is an image of a head, and the 2 coordinates in this manifold are the head left and right rotation. And so this example is here to show that in addition to reducing dimension, what we would like is to understand the manifold. So understand how rotation left, why rotation left, and understand that these 2 coordinates have a meaning at the rotations of the head. Okay, so now let's start with the definitions. So there will be a section on definitions, and then we will continue with the actual manifold embedding algorithms, and we will stop somewhere probably before the end of this section. So here I'm going to present the definitions in an intuitive way so that we can progress faster. However, in your notes, you have the mathematical definitions for everything. So first of all, what is a manifold? And a manifold is something that can be represented locally as a piece of a Euclidean space of Rd. Yes, and this is what this figure shows: is that if we take a nonlinear manifold, we cut a piece of it with a ball. So we have a small neighborhood on the manifold. This maps smoothly to a piece of R2 in this case. So it's a set and I'm putting this silly mark here. It's like RD, but only locally, so on a neighborhood. The chart is something that represents this relationship more exactly. So suppose we have a neighborhood U in the manifold. Then there is a coordinates chart, and let's call it X, for example, that goes into V, a subset of RD. And this function has to be invertible, and in our case, it also has to have to be smooth in the sense of having differentiable. And that is called a diffeomorphism. A manifold doesn't have to be always smooth, but in our cases, we are going to assume that it has derivatives of any order that we want. Yeah. Okay. And a chart, in a chart, we take, for instance, a point P on the manifold. Here is a P, and we map it to X of P, which is a set of coordinates. Yeah. Okay. All right. Now, what is an atlas? An atlas is just a union of charts that covers M. And we are not going to use the chart and atlas very much. So atlas is yes. And this picture shows how an atlas is used. We want to cover M with charts so that every point in M is inside a chart. This every neighborhood U is by definition an open set, and so it means that the charts have to overlap in some places. This is in that case, every point in overlap will have more than one coordinate function. Yes, but this is part of the definition of a manifold. Yeah, it's inescapable. We are going to use most modern manifold learning is done essentially assuming that we are inside a single chart. And so we are not going to have to bother very much about how to do this transformation of coordinates from for points that are in two charts, like which one to use and so on. This is not our concern. Okay, but what I want you to remember is that every place in a manifold is inside some larger neighborhood where it has coordinates, and these coordinates are d-dimensional. The D in the definition of the manifold, it has itself a name, and it's called the intrinsic dimension. Yeah. Okay. And because typically not in mathematics, but in manifold learning, our original data is already in some high dimensional space, capital D. Capital D has the name ambient dimension. So it's the original dimension of the points. Let me see if there are questions. Now, what else do we need to define on a manifold? At every point of a manifold, there is something called the tangent subspace. And the tangent subspace is exactly what you imagine. It is a vector space. So for every P in the manifold, we have T sub P of M. It's a very funny notation. And this is a vector space isomorphic with RD. Yes. And the picture on the right shows how we imagine it if the ambient dimension is another RD. Yes. And in the notation T of M, which you may or may not see in this course, is basically all the tangent space. It's called the tangent bundle. Yes. So we assume that at every point on a manifold, we have a tangent space, which is a vector space. Now, what is in this vector space? Or what is its role? This vector space contains the tangents to curves in the manifold. That is its intuitive meaning. And in particular, some of these tangents are tangents to the coordinate curves. Yes. So, and these are written as dx. So x is in RD. X of P is in RD. And so it's a vector. Let's denote it to be consistent with the picture. Let's denote x of P as UV, for example. Then dx du at P and dx dv at P are both vectors in the tangent space. And not surprisingly, you can guess that they form a basis for the tangent space. Yes. So we see that there is an intimate relationship between the coordinate functions on the manifold and basis in the tangent space. Yes, or you can think of the tangent vectors in the tangent space as velocities on the curves, or as gradients of functions on the curves. Yeah. So this is how when we work with a manifold, you can include the gradients and derivatives through the tangent space. So the derivatives of scalar functions on the manifold will be in the tangent space. Okay, and so we are almost finished with the definitions. The third definition is embedding. What's an embedding? As I said, most manifolds, and examples are coming in the next page, need more than one chart. If they needed only one chart, they would be equal to RD, and so it would be less. We wouldn't be doing such interesting things. And but we can, this is used in manifold learning. One can circumvent the use of multiple charts by mapping instead of RD in some M larger than D. Yeah. So we can take a function phi. And this phi is smooth in the sense that it has derivatives of any order we want. we also assume that phi is invertible and its inverse is also smooth. Yes. Then we have a one-to-one correspondence between the original manifold and its image through phi, but its image through phi is in m dimensions. So we have effectively reduced the dimension from Rm, from the original Rd to Rm. Yes. So this is a method of performing dimension reduction without getting all the way down to the intrinsic dimension. What we lose is the fact that now we are in another ambient space of dimension m, but this dimension is much smaller. How much smaller can it be? There is a theorem, a celebrated theorem in mathematics called Whitney's embedding theorem, which says that m can be of the order 2D. So if we have 60 dimensions, but the intrinsic dimension is 2, then it means that we can obtain an embedding that has dimension at most 4. Yeah. So we can obtain very significant dimension reduction without worrying about charts. And what is called classical manifold learning algorithms, and in fact, a better name for them that you'll encounter in the course is embedding algorithms. They, as the name says, construct embeddings of the data. So if you have encountered manifold learning algorithms before, the chance is great that you have encountered embedding algorithms. Yeah. So now let's look at some examples, some working examples that we can carry with us, simple examples. One simple example is RD. Yes. Is a manifold with dimension intrinsic dimension d, trivially. Yeah. Or any segment, open or closed, of RD is also a manifold. Yeah. Another set of simple examples are the circle. Okay, the sphere. I don't know how to draw it better. Okay, and in general, SD, sphere of dimensional D. Okay, and notice that all these spheres must be embedded in D+1 dimension. Yes. So if we want to obtain by manifold learning an embedding of the sphere, we obtain one in, we have to have M equal or larger than D+1. Yeah. Another set of very simple examples are the tori. So this is the, let's call it T2. It's the torus. Yeah. And there is something called T3, the tree torus. And so on. We can have tori in D dimensions. How do we define a T torus? The two torus is generated by two circles. Yes, and let's see. One of the circles is this one. And the other of the circles is this one. Yeah. And so these are the circles that generate the two torus. For the three torus, this is generated by three circles, and so on. So the dimension of the D torus is also D. and it needs d+1 coordinates to be embedded for an embedding. Yes. Okay. Let me give you another example of a manifold that will appear in our examples. This manifold is a subset of RD. Okay, but it's then it's deformed in space. Yeah, and that is I think the filter will hide this image, but I hope you can see that it's a piece of paper with maybe with a boundary, with or without holes of any shape. So it's like a connected surface, a hopefully open set in RD, in low dimensional set that can be then mapped in higher dimensions. And if you are familiar at all with manifold learning, you must have seen the Swiss roll, and that is just this piece of paper rolled about in a spiral. Yep. Okay. So I'm going to modestly try to attempt to draw this. It's going to look like this. And I'm going to draw the borders dotted because I want to make it an open set. There is something called manifolds with border, and they're not difficult to study, but I'm not going to talk much about them. I just want to say that they shouldn't be an issue. So this is a set. This is a set in RD that is then mapped to high dimensions. Yeah. These are all examples of low dimensional manifolds. Let's give some examples of what is not a manifold. And what is not a manifold is something where either the dimension is not constant, or the dimension is not constant because two constant dimension manifolds intersect, or this would be non-smooth. And this is also something that we are not going to do it, not going to study. Non-smooth manifolds are, for various reasons, not treated rigorously in our framework. So here is an example of what's not a manifold, something like this. Yeah, because here the dimension is 2, and here the dimension is 1, or something like this, because this point doesn't have dimension 1. In fact, it doesn't have a dimension. It can't be mapped smoothly into R any real value, or something like this, because so this is a manifold but it's non-smooth. Yes, which means that we would have a map that maps this into R1, but this map will have a discontinuous derivative at this point. Yeah. Let me see now if there are questions, because we are going to start with manifold learning learning algorithms, and it would be nice to hear if that the bases are covered. So I'm ready to take questions. Okay, feel free if you need to ask a question about something that was back, feel free to interrupt and or to ask them next time I ask questions. Okay, so we have now discussed, have the basic definitions. We have some motivations. I hope I convinced you that it's useful to do manifold learning. Now let's see how we can do it, what kind of algorithms we have. And this is a super busy slide, so we'll take a time to go through it. First of all, what is the paradigm that we are working on? Yeah, so let's look at this part. What what is it that a manifold learning algorithm does? Before we talked about mathematics, mathematical objects like manifolds and tangent spaces. Now we have data. Yeah, and these are points, and these are the points that are d-dimensional, but we assume they are from a manifold that is lower dimension. Yeah, and what we want is to map these points that we are having, these high dimensional points, to a lower dimensional, lower dimensional coordinates in Rm. So we want to obtain an embedding of the points. But what is an embedding of the points? It's just a mapping, and this mapping is denoted by F. However, we make the additional assumption, and this is actually proved by people who do theoretical manifold learning, statisticians. For example, we want to make the additional assumptions that if n goes to infinity, if we gave the same algorithm the whole of the manifold, not just a sample of the manifold, then we would get an embedding. Yes, so we run some algorithm on finite data. We assume that there is a limit of this algorithm when the data is infinity, and that limit of the algorithm is an embedding of the manifold. Yeah, so embedding is a mathematical object, and the algorithms work on finite data. So there is this assumption of the limit. And so when I say that, since, for instance, isomap or diffusion maps is a smooth embedding, and when I say that Tisney, for example, is not a smooth embedding, that's in the sense of having an infinite sample from the manifold. Yeah. If F is a smooth embedding, then we are going to say that F recovers the manifold. And there are three. Okay, are there questions here? Okay, there are three principles, three big principles for every relevant manifold learning algorithm. One of them is, one idea is to do something that we have known for a long time. Let's do principal component analysis locally around the point. And that will map the point in RD smoothly. The second one is called principal curves and surfaces. And this is actually a very interesting algorithm I'm going to present. I'm going to present all three. And the third one is the embedding algorithms proper. So these are the algorithms that you may have heard of, like diffusion maps, Laplacian eigenmaps, isomap, and I want to highlight also LTSA. Why don't I highlight more? I'll explain at the end of this lecture, or maybe next time. How much time do we have?
About 15 minutes.
About 15 minutes. All right. Okay. Now, before we go into studying the algorithms, let's look what makes the problem hard. Yeah. And first of all, we don't know the intrinsic dimension D. Yeah. So we have to estimate it somehow. In this course, we are going to assume that it is known. And by the end of the course, I will explain what is known about estimating the intrinsic dimension. The bottom line is that intrinsic dimension is easy to estimate, and easy means we don't need many points to estimate it if the data come from a manifold that is not noisy. However, if the data come from a manifold that is noisy, I consider it an open problem. I have tried the best methods that I knew for the dimension estimation on the data that I showed you, and the algorithms do not give the correct answer when the correct answer is obvious from all the other reasons. So, so we are in between. If the noise is low, then this is an easy problem. If the noise is hard, then in addition to running a dimension estimation algorithm, you have to look at other geometric evidence about the dimension of your data. Okay, this is not as hard as it looks, because in practice we are not going to be able to estimate for a long time any manifold that's not in dimension that's long. Yeah, so the algorithm that I'm presenting will estimate and will be successful in dimensions 2, intrinsic dimension 2, 3, maybe 4. However, after that, it's not sure what the algorithms are doing, and I do not know about examples where they have succeeded and have been verified rigorously. Yes, so what you can tell rigorously about an algorithm stays in very low dimensions. And in very low dimensions, you can actually use other ad hoc or careful validation to know what is the actual intrinsic dimension. Yeah. Now, why can't we go past such small intrinsic dimensions in this field, or at least not reliably? That's because this is a non-parametric problem, and you'll see this on the next slide. Another thing that will come up when we talk about estimation algorithm over and over is that we are working with samples here. Yes. And these samples are sampled from a distribution which may not be uniform. Yes. So in manifold estimation algorithm, we have always to keep in mind the sampling distribution. And tomorrow you'll see what influence this can have. And I'm going to denote it by P. I'm going to always put a parenthesis so that you don't confuse it with P, the point on a manifold. Okay. And another element, another difficulty in estimating manifold comes from the injectivity radius. And people or reach. Yes. Now, intuitively, this injectivity radius is almost the same as what people denote intuitively by curvature. I'm not going to talk at all about the curvature in the mathematical sense, but I'm going to exemplify what injectivity radius means. Okay, and so let's look at a little bit at what injectivity radius is. Yeah, that is the if you have a manifold like this, injectivity radius is the smallest tube that I can build, is the radius of the smallest tube that I can build around the manifold that is not self-intersecting. So if I build a tube of this size, this tube will be self-intersect, and so this is not the injectivity radius. So let's pick a tube that's smaller. This one. This has no self-intersection, and so this is this gives me the injectivity radius. And let's call this is called tau. Yeah. All right. And notice that we can have small injectivity radius can happen in two ways. Either because the manifold comes close to itself, like this, or because the manifold has very high curvature, like this. So here again, the injectivity radius is small. Yeah. And what this means is that in these regions, we need a lot of data to estimate the manifold. So in these regions, we need very dense sampling. Otherwise, we are not going to estimate the manifold correctly. Yeah, and this is what makes injectivity radius be a challenge for manifold embedding algorithms. Yeah. So it has to do much more with it has to do a lot with the sampling of the data. Okay, and an essential parameter that will come up also very soon lecture 3 is probably tomorrow, is the neighborhood radius. So what is the neighborhood radius? It will come up the definition will come up shortly. So we are going to talk in the time that is left about what is non-parametric estimation and the neighborhood radius, and maybe do a quick dip in estimation algorithms for manifold. So what is parametric versus non-parametric? A parametric model is, so assume that we just do density estimation. Assume that we don't have a manifold at all, just this very simple problem of having a density estimator. We can have two kind of density estimators. One is assuming that the density is Gaussian, then we fit mu and sigma squared, and these are the parameters, and we get the density. Or we can do something called kernel density estimation. And some of you may already be familiar with kernel density estimations, others may not. And kernel density estimation is an operation that basically takes a kernel, and the kernel can be the Gaussian again, and places a kernel on every point rescaled by some h, and you can see that h is actually the variance of the Gaussian. Yeah. Now, this estimator is much more powerful than a single Gaussian estimator because it can actually model accurately a density of any shape if we choose the kernel width small enough or appropriately. Yes. So this kernel density estimator has no restriction about the shape, whereas the Gaussian has a very strong restriction of the shape. It's just a category of bell-shaped distribution, the Gaussian distributions, and this makes a difference. So this is a fixed shape, and kernel density estimator can estimate the distribution of any shape. But the difference that it makes is in the rate of convergence of the parameters. So you may know that when you estimate mu hat, this estimator is unbiased, and its own standard deviation is proportional to 1 over square root of n. Yeah. Which means that if I want an estimator to be 10 times more accurate, I have to increase n by 100. Yes, to get another decimal point in accuracy of estimating mu, I have to increase n by 10 to the power 2, which is 100. Okay, this may look a lot, but it's actually the best possible rate in for these parameters, and it's called parametric rate. Well, except for other assumptions. These estimators that are called non-parametric, which allow you to estimate any shapes or which are much more flexible, do not achieve this rate. Estimators that are non-parametric achieve rates that are slower. So this is n to the minus 2.5, 2 over 5. This is a larger negative, this is a smaller exponent of 1 over n. And so if we compare how many more samples I need to just get 1 order of magnitude increase in accuracy, for the same estimator with KDE, I need 300 instead of 100. But in higher dimension, this gets worse because for the parametric rate remains fixed at n to the 1 over 2, whereas in higher dimensions, this multiplier becomes huge. Yeah. And manifold estimation is a non-parametric operation. We assume that the manifold can have any shape it wants, except it has to be smooth and have a reasonable injectivity radius, a bounded injectivity radius. Otherwise, it can have any shape. And under these assumptions, our rates will be similar to kernel density estimation. In fact, manifold learning can be thought of a fancy kernel density estimation in some sense. Yes, and so this means that the number of samples needs to grow exponential in the dimension to increase accuracy. That is the main problem with the non-parametric estimation, and sadly, manifold learning does have the same characteristic. Yeah, so if you want to remember something else than the mathematics and the definition from today, please remember the fact that if the intrinsic dimension increases, then the number of samples for estimating manifolds has to increase exponentially. What is nice is that a good, well-designed manifold learning algorithm of any kind will only depend on the intrinsic dimension and not on the ambient dimension. So well-designed manifold learning algorithm in high dimensions essentially depend on the intrinsic dimension and ignore the dependence on the large ambient dimension. Okay, it's a good time to see if there are questions.
Thank you, Marina. I think it's quite clear to me, probably for the rest.
Okay, do I go for another 3 minutes or do we stop here? What do you say, Akram?
I would say let's go just five more minutes to, since we've lost a little bit, and then, yeah.
Okay, so one more important concept is the neighborhood graph. And this can be seen in the notes or in pictures. Here is our data, a point cloud, that's how it's often called, of endpoints in high dimensions. The first thing that we do, that every manifold algorithm has to do, is to find the neighbors for every point. Yeah, and we can define neighbors in two ways. Either we define neighbors to be all the neighbors inside within a radius, within a distance r from a point I, and this is the radius neighbor graph. Or we define the neighbors to be the k nearest neighbors of the point. Now, you are going to see in many research papers, algorithmic papers, that this makes no difference. It actually makes a very big difference in certain situations. In others, it doesn't. In a nutshell, for k-near neighbors graph has many computational advantages. In particular, if we fix k, and we will fix it not to 4 or 5, but to like a multiple of the dimension. So maybe 40 or 50, yes? But if we fix k, then every point has the same number of neighbors. And the graph is always connected by definition. And if we have to find efficient algorithms for finding these neighbors, there is much more software available for this. And we'll have to, because finding nearest neighbor in high dimension is a hard problem, computationally expensive. It's a bottleneck in manifold learning, actually. Okay. However, for certain operations, consistent estimation is only assured if we use the radius neighbors. So in the rest of this lecture, we are going to only use the radius neighbors. Okay. For the radius neighbors, we need to choose the neighborhood radius R. This is something that we are going to talk about tomorrow. But if we choose the right radius neighborhood, then we construct this graph. And in addition to this graph, we also construct a matrix of distances. Yes. And this matrix is sparse because we only care about the distances between neighbors. We do not care about distances between points that are not neighbors. Yeah. And this is the last idea. The last idea is as follows. After we have done this, after we have found the neighbors for each point and calculated the distances between neighbors, only between neighbors, that's why this matrix is sparse, then we can throw away the original data. All that the manifold learning algorithms need to know from here on is the graph and the distances between neighbors. This is the only information that is passed on to whatever algorithm we are using. And that is very important to remember, that this distance information is whatever is enough to recover the intrinsic geometry. And that's what I mean by intrinsic geometry. I'm going to take this sheet of paper again. In a manifold, we only care about, let's say, curves and distances along the manifold, but we never care and we never want to reproduce the distance between these two ends. Yeah, this is extrinsic geometry. And the manifold geometry and all the concepts that we want to learn about the manifold are not related to the deformations of this. Yeah. We want, in fact, manifold learning wants to filter out not just the noise around the manifold, it wants to filter out this deformation and bring us back to a low dimensional RD. So again, I'm going to repeat the last point, which is that the information that we need for manifold learning is summarized by the neighborhood graph, the neighbors of every point, and the distances between these neighbors. This is can be slightly amended, but no matter how you amend it, it is the information that is really used in manifold learning. Just distances between neighbors, never distances in space, in the large distances in space. And that is actually the power of manifold learning too, because it can recover from it the information that is more stable and more robust in the data, yeah, which is paradoxically at the smaller scale. Okay, thank you very much. And I see there is a question in the chat. I can answer it.
Thank you, Marina, for this excellent lecture. And yeah, so